Okay, we're on, I think. Hello.
Hello, everyone.
And welcome to this. We're going to be talking in this webinar about online testing of online PD testing of cables. As soon as we said we were going to do this subject, we just thought this is a big one. We could be here for all day. So this is going to be a relatively quick run through of online testing of cables. This is a topic that taxes quite a lot of people, and like I say, we could be talking about this for hours really, but hopefully we'll give you a good overview on this. So thanks everybody for joining and welcome. So see if we can get that going. So the contents of the presentation today, we're going to talk about why we test on cables, just very briefly on that, and quite some interesting statistics on some of the failure causes that we see on cables. We'll briefly mention the difference between the different types of cables, paper cables, XLPE cables, and the relevant tolerances in how they deal with PD. Talk about cable terminations. It's that whole grey area, what is actually switchgear and what is actually cable. When we've got switchgear plant people, they don't want to own the cable termination, and the cable engineers don't want to own the cable termination either, because that's where most of the problems occur. So we'll talk about cable terminations, and then I'm going to hand over, and Brad is going to talk about looking for PD down the length of the cable. And throughout the presentation, and particularly at the end, we've got some case studies and questions. We can take questions at the end, but if you've got anything burning, any burning question at any time, then you should be able to use the question dialog box and shoot that through, and either Brad or myself will try and answer as we're going along. Okay. So why test for PD on cables? I mean, relatively obvious, and the same for why we test for PD on just about any other HV electrical asset. Cables is an interesting one though. We've got large networks of cables. Often in the countries that we're dealing in, we've got quite old networks now, some aging networks. We've got different types of assets, different types of quality. When XLPE was first started introducing into the network, there was maybe not so well understood in the way the manufacturing would happen. Not so good quality cable was going in. So we've got different types of cable, the XLPE, the PILC, the quality of that, different manufacturers going in there. Once you tend to install the cable, then it's very much almost a case of fit and forget. So you've got the cables, they're directly buried. There's no visual examination you can done. There's no maintenance and things like that. So how do we know the condition of our network? And if we've got an aging network, so we've got cables 40, 50 years old or older than that, and we've got large distributed network on that, how are we going to make an assessment of, have we got a bow wave of failures that are going to come up? And what we do know from statistics in different countries, different parts of the world, is that cable failures have a significant impact on the overall network performance. So the failures will cause you a significant proportion of your customer minutes lost, or your SAIDIs and your safeties. So they're an important part of the network, and we've typically got relatively little condition data on that. Overall, why we do partial discharge and condition monitoring is always, as we say about cables, switchgear, transformers, or anything, the three main focuses for us. So we're looking for increasing safety, improved asset performance, and of course a financial benefit of that. When we're talking about the terminations, with the terminations in the switchgear, in the substations, then of course the safety aspect can become significant. So you can see the picture on the right. In this particular slide here is an old compound insulated cable box which has exploded. If we're in the substation at that time, then obviously we've got a safety aspect. The picture in the middle there is of a joint that has failed. Now, if that's going to fail, it's directly buried, it's underground, we're not realistically going to get much of a safety impact. We're going to get more of a network performance impact. So traditionally, what a lot of companies have actually done is thought about the fact that we've got the cable, it's directly buried. We're just going to wait for it to fail. Once it fails, we're going to have to dig up the road. We're going to have that outage, move the network condition about and everything else. And we're not going to save much money by just letting it fail rather than being proactive. Lots of studies have been done around that, actually, on the actual cost benefit of that. And due to the proportion of cables affecting the network performance in the SADIs, when you look at the study, what the statistics generally show is that if you can proactively replace a failing cable or a failing joint, rather than waiting it to fail, you will typically save around 30% of the cost, or 33%, a third of the cost of letting it fail and fixing it. And that can be much, much greater depending on what it is. But the fact of a planned outage versus an unplanned outage typically will give you at least a 33% saving. So for looking down cables, it's more a case of a financial benefit in the substation. Then we've got that increased safety benefit as well. Now, let's looking at some statistics on from forensic investigations of failed cables. So these are cables that were taken into a lab and people wanted to know how they're failing or what was the root cause of the failure. So when it's particularly obvious, say a digger has dug into your cable, then these are not the ones that we're going to forensically examine. So you may have a slightly higher proportion of failed due to external damage than we're showing in this particular graph. But if you look at the statistics here, what you can see is the overwhelming cause of cable failures when we've done forensic investigations is all revolving around workmanship. So error in how things are put together, and whether the joints or whether the terminations. However, the manufacturing defects are not insignificant at 16% in this particular graph. External damage in this particular instance, not a massive contributor. What we have found is that age-related failures are relatively small, but are starting to increase as networks are getting older. Looking a bit deeper into that set of statistics that was put together, the references down the bottom here, is that what we find is that there is a significant proportion of infant mortality failures generally in the first 10 years, and that absolutely lines up with the fact that the workmanship issues. It's not an easy case. There's so many things that you have to consider when you're doing the joints. You've got different types of kit, different joints going on the network, levels of training, experience you're doing it in a hole. Dirty with all the weather around you as well. So it's not surprising that you can get defects creeping in at that stage. Once you've got through that, maybe the first 10 years or so, then we get random failures over the next, say, 30 years. And what we're starting to see is a slight increase, an uptick towards the end as the cables start moving above 40 plus years, and we're starting to see more failures occurring. So that is of course a bit of concern as we got aging networks. Now, partial discharge in cables will affect all the different types of cables, so but it will affect things slightly differently. So if we look at the top picture here, is a treeing that we can see in a paper insulated cable, and what you find with paper cable is it's got a little bit more tolerance to partial discharge. So it may take longer for PD, and that PD may have to be at a higher level before you get a cause of failure. So on PILC type cable, you can find partial discharge inside the cables, and as well as at the terminations and at the joints and accessories. When we start moving on to XLPE cable, again, we can get partial discharge occurring. Once you get any length of electrical trees in the XLPE itself, that will accelerate away to failure very, very quickly. So typically for an XLPE system or XLPE cables, what we're really testing for when we're testing partial discharge is really partial discharge inside the joints and the terminations, more so than trying to test inside that the bulk of the cable. The failures will occur very quickly if they've gone to a PD failure inside the bulk of that cable, and so a periodic testing may not have give you the situation of trying to find that. So if we've got a relatively short run of cable, we've got no joints in between, say the switchgear and the transformer, two substations, then just testing at the ends at the switchgear and the terminations is probably effective enough for you. When you've got a longer length of cable and you've got joints in between, then we need to start looking at different techniques, and that's what Brad will talk about in a while. Now, the levels of discharge that we can, or that cables can tolerate, and what we see as thresholds for concern, are shown here in this particular table. This was built up over many years. So EA Technology has been testing, offline testing cables since late 1980s or 1980s, and then online testing of cables has come in over the period of time as well. And when we add all this together, we can see that these are rough thresholds that we use for a guidance of what we consider serious and not. So you can see that there's a significant difference between the PILC cables and the XLPE cables, and between the cable itself and the accessories, which are generally the joints can cope with a little bit more discharge. So major concern levels for XLPE will be, say, 2,500 picocoulombs on the joint, and for a PILC cable will be up to 10,000 picocoulombs. The PILC cables can cope with certain levels of discharge inside, particularly maybe the belted cables that we had in there. Again, generally used to put them into the network. The belted cables would discharge when they first went in. That would tend to even off after about 18 months or so, but they can cope with a certain level of partial discharge, whereas XLPE can. So they're the sort of thresholds that we use as a guidance when we're testing to see what we want to investigate, what's of relative concern we monitor, and what we think we're quite comfortable with. So let's quickly look at the cables, detection on the cables and the cable terminations, starting with the terminations in this particular case. Now, PD, quick recap on the different types of PD. We have three main types of partial discharge that occur. Stuff that happens deep inside the solid insulation, so internal discharge. Stuff that happens across the surface of insulation, surface discharge. And we get corona discharge, which is the sharp point into a gas. When we're starting to talk about cables, cable terminations, then really the only two that we're significantly interested in is the internal discharge and the surface discharge when we get to the termination point. The techniques that we deploy for this, irrespective of what type of plant we're testing, we use the transient earth voltage, which is an electromagnetic technique, generally in the HF to the VHF range, and that's for detecting the internal discharge and high-level surface discharge to earth. What we use with the TEV technique also is localization. We use time of flight for direction localization. So from that we can say, is it coming from the cable termination, the switchgear, or is it potentially being imported from up the cable? So that's how it gets applied for the in the cable context. Ultrasonic, directional, pointing in towards termination. This is not going to help you for testing down cables, but it is a significant failure proportion of, say, dry terminations at the termination point where we've got cross phases, for example, which we'll come to later. If we're looking down the cable, we're trying to see things that are happening in joints, not so much in the terminations, then applying either a radio frequency current transformer or high frequency, some people will call that current transformer, will allow us to look further down the cables. We'll see later that we do actually test all the way down to, say, around 500 kilohertz and below, which is where not in the HF range. That allows us to test further, and Brad will talk about that. UHF technique is the final technique that we use for detecting of PD. Often that's used on high voltage open terminal type switchgear, or where you can't use TEV. Where it can be a potential use in this particular instance is for testing maybe cable joints inside pits, where you don't want to be going in the pit first and you don't want to be touching the TEV probe against that, or you wanted to do a PD test from a bit of a distance, then we can use the TEV, the UHF technique, or for localization. So UHF signals won't travel anywhere near as far as VHF signals. So if we're finding the problems, say at the switchgear, at the termination, or around a particular joint only, then that gives us an indication that it's happening in that location and not something that's being imported. So that's the different techniques we deploy.
If anyone wants to ask a question, there's an orange arrow on your control box there, and that'll open up a dialog box, and you can type questions there if you need to.
Okay. And if you don't have any questions, that's fine.
Yeah.
So cable terminations or cables, sometimes it's pretty obvious. So in this particular instance here, we've got a case study. It's on a 13.8 kV transformer, and we've got ultrasonic coming out of that cable box. We can hear it. We've got transient earth voltage. We've got 15 decibels and about 4 pulses per cycle, quite a high rate of discharge for that. So we've got some component that's flashing over to earth. If we get ultrasonic signals coming out of a cable box, we've got a problem in that termination area. It's pretty straightforward in that. We open this particular one up, you can see we've used the wrong component, or somebody has installed the wrong component. We've got those two, the boots touching each other, and we've got PD between. We've got lots of nitric acid and ozone building up, and you can see all the rusting inside that cable box. Relatively straightforward, not something we've seen that a few times. I just saw a new example of a very similar way of being using the incorrect boots inside a termination just last week. So that one's pretty obvious. It's a termination, we need to change it. The other area that really sprung up when we started moving from compound insulated to dry terminations, whether heat shrink, cold shrink terminations in the say late 80s, early 1990s, we had an uplift in the level of failures on the network, and that was due to the misunderstanding really about the level of spacing required and whether you can cross phase and things like that. So in these particular two instances, we've got somebody knitting cables on the left hand side, and again the ozone producing is completely rusting up that cable box. On the right hand side, it's not quite as clear to see, but the spacing down towards the crutch area is inadequate. That is discharging one phase to another, causing ultrasonic surface tracking, and that will eventually cause failure. It won't take too many more years. It will accelerate away and cause a failure in that particular place. Those sorts of defects are generally only found using ultrasonic techniques. It's a surface type defect, phase-to-phase discharge. You've not got a massive component to earth. The easiest way and the typical way of finding that is just to use ultrasonic testing at the termination box. It gets a little bit trickier when we start seeing partial discharge inside the cable around the termination area. Now, often, as in this case study, what we see is we start seeing a failure, and then we start seeing maybe a population of effect happening, or a site effect. So if we look, we think back to our statistics where a lot of problems are associated with workmanship, but then there's also problems associated with maybe design defects and things. What you can often find is that you get a type defect occurring in the locality caused by maybe the jointer is not 100% familiar, or is doing the incorrect procedure joint after joint. So what we often find is that you'll get cluster of events around a particular area. This is one of those situations. We've got a plug-in 33 kV plug-in type termination here in the picture. previous failures had occurred, so that instigated a program of regular spot checking using UltraTEV +2, so the transient earth voltage ultrasonic. No ultrasonic ever detected, but testing on the outside of these cables, which again, going back to the previous webinars we've done, if you can test one place, always make sure that you place the TEV probe on the outside of the cable where you can see that, because that's a really good area for getting the coupling of problems coming from the terminations, but also actually coming from the switchgear itself. So in this particular example, we've got 3 indications of reading, and on one of the phases here, on the blue phase, we're getting over 30 decibels. What I would say in this particular instance is, if you have indications, you're starting to see terminations failing on particular types of switchgear or particular locations, don't be absolutely beholden to the amplitude and the thresholds. It's more a case of identifying the discharge, the fact that you've got discharge in there. Certain defects may not produce very high levels of PD before they fail. So if we're starting to see a population issue and we start seeing PD, maybe we're only seeing the 23 dB here. If we've had previous problems, then that's something that we would take much more seriously than if we just saw it as a one-off sort of test here. The terminations can generally not cope, or dry terminations will not cope with the partial discharge levels of, say, an old compound insulated type terminations. So any level of discharge where we know that we've had previous failures, we start getting a little bit more concerned. In this particular instance here, because of those previous failures, they took that cable termination out. They actually took all 3 of them out. The one with the 32 dB was found to be discharging. The other 2 were found to be free of discharge, and it was confirmed that there was a particular type of the way the termination being put together was incorrect, and basically there was a difference between the XLPE and the screen with greater than 2 millimeters, which is much more than the specification. You have to follow the jointing instructions. They're all there for a particular reason. Using the right screen, following the jointing instructions, so very important. So this particular one had been made incorrectly, started discharging, population issue. So you can see we could easily find that, and we could take action and prevent that failure without using any equipment other than what we typically use for testing switchgear. So I'm just going to hand over to Brad, we're going to swap seats. Talk about cable PD.
No worries, we just had one question come through and I've put the answer through to everyone.
Okay.
All right, so now let's talk about cable PD. So Neil has spoken a lot about finding cable PD in the terminations, but what about when the cable PD isn't in the termination? What about when it's down the cable? Okay, so I'll get to the next slide here. So when we've got PD in cables, we've really only got one, well, most of the time you've got one spot to test, and that's at the ends of the cable. So at substation A and substation B. You test for your termination cables there. You can do TEV testing at those ends of the cables, and you may be seeing cable PD coming from down the cable, or it may be coming from up in the switchgear, or the overhead connection, whatever your cable ends up connecting to. So what we utilize is being able to use test instruments at either end of the cable to see what we can see. So when you have PD on the actual cable itself, the PD will emit high frequency signals that will travel away from itself like a ball of energy. Very similar to the TEV technique, where when sparks are happening, every time a spark happens, it will emit energy, and the energy will radiate away from itself. So on a high voltage cable, that energy will travel down the left and down the right of the cable away from itself. It'll induce its energy into the cores of the cable and into the screens and armors of the cable, anything that's conductive. So So what we do to capture those signals is, when we're testing with RFCTs, that is we will put an RFCT at the end of the cable on the earth screens, and you attach it around the earth screens. We've got a few pictures of that coming up in a sec. And when our RFCT is connected on there, it will detect high frequency pulses that are bouncing up and down the cable. That's the easiest way to think about it. So what I've got here is a video showing a PD site and the signals emitted from that, and then how our instrumentation will collect those signals. So just pretend there's a PD site there. A pulse gets created and it will travel away from itself in either direction. And those signals will bounce up and down the cable. But as it reaches the far end or the near end of the cable, it will create a pulse. And then the second pulse comes that's reflected off the far end of the cable. It will come to you. You'll see that pulse again. And then the first pulse that you saw will go all the way to the far end of the cable and bounce back to you again. And in a stereotypical example, you'll see the first pulse, which is the actual PD pulse. The second one is the distance to the PD, and the third one is the distance to the far end of the cable. And we use that information to figure out what's going on. So if we go to the next slide. So that's what it looks like on a piece of paper, but in real life, it looks like the trace you can see in the bottom right-hand side of the screen there. You can see a sharp pulse that's first come to you. The second pulse is the second reflection, and the third reflection is the distance to the far end. So this is very similar to TDR. Well, it's the exact same theory as time domain reflectometry, if anyone wants to Google that. But it's signals bouncing up and down cables and bouncing off changes in impedance. So these signals can be affected by the type of cable, the length of the cable, the loading conditions, and the propagation characteristics that they travel through. So when you have a very noisy cable, so as we all know, our 50 Hertz and 60 Hertz networks, everything's connected to everything. So you will have a lot of noise traveling through these cables and bouncing off substations and going, you could have noise from overhead lines, from mobile phone towers, whatever's out there creating signals. And what we need to be able to do is see through the noise. And we do get affected by noise a lot. So one way we see through the noise is by filtering, which I'll talk about in a sec. So what we do for the way that our partial discharge traces are analysed, I suppose, is we look at, we come up with a picocoulomb level, or we really come up with a coulomb level, which is a measurement of energy, but a lot of our measurements are measured in picocoulombs, nanocoulombs if it's really high. The way that we come up with that number, or the way that everyone comes up with that number, is to measure the area underneath the graph, underneath that first pulse. So if you can see on the left-hand side of your screen there, you can see that red area underneath the first pulse. So that will give you your picocoulomb level. And then on the right-hand side, on that second graph, we measure the distance between the first pulse and the second pulse. That will give you a distance percentage-wise of the cable from where you are testing to how far down the cable the PD is occurring. And then the third pulse is the length of the entire cable. So we use all those characteristics to come up with answers. We'll also get a phase resolved partial discharge pattern, as we will see in a sec. So this is the main piece of instrumentation that we use. It's called the cable data collector. What you have is a piece of hardware in the middle there. You've got 3 RFCTs and you connect all them via leads, and those leads are connected back to a laptop. On the laptop, you have a piece of software that you type in who you are, where you are, what you're testing. It's important to input the length of the cable that you're testing. If you know that before you're testing, it's very useful. But once you hit go on the software, it'll take anywhere from about 7 to 10 minutes to capture the cable PD signals that are bouncing up and down those cables, and then you can move on to the next set of cables and map your network out. We find that it's best to test all your cables from both ends if possible, and then that data is analysed off-site. So when you're out in the field, you use this instrument to very much capture the data and then analyse it off-site. Okay, so one of the limitations with using RFCTs is having access to the earth screens of your high voltage cables. So the best spot to test is just example on that in that right hand side there, where you can put your RFCT around the earth screen, making sure that that earth screen doesn't have any other parallel paths to earth. And what I mean there is a common problem, or not a common problem, but a common example of that is when you have a PILC cable, and that cable is terminated and plumbed up at the bottom of a switchboard, and that plumbing will actually be touching the steel metalwork of the cable box that's terminated into. But it will also have an earth screen that goes off to the right and gets connected to earth. So what you have there is if you can imagine, the signals are coming up the cable, radiating away from the PD source. Some of those signals will travel down the earth screen, but also some of them will travel through that plumbed up connection onto the termination. And in that instance, it's pretty much a waste of time running that test because you've got two parallel paths. You only want to test where all the signals can go through your RFCT and you can capture all of those signals. Now, with a lot of modern day construction, you don't get access to those earth screens because they're all built and terminated inside the cable boxes. So that is one limitation to using an RFCT. It's just the way it is with modern day construction. We find that some people do design their networks to have the cable earth screens come out of the cable boxes and get earthed externally to the cable boxes, and that's exactly for this reason, so that people can come along and hook on an RFCT to better understand the condition of their cables and the nearby assets for PD activity. Okay, so in this slide we've got two examples of what it looks like in the real world when you're hooking on the RFCTs. So on the left hand side we've got red, white, blue cable terminating onto a piece of switchgear there, and the three RFCTs are hooked easily onto the earth screen. So that's a perfect setup for capturing cable PD signals. On the right hand side there, it looks a lot busier, but it's doing the exact same thing where we're putting the RFCTs around the screens that are coming off each cable core. In that instance, it looks like there is multiple earth screens coming from the same cores.
Yeah, we've got. I think in that particular instance, they actually did have for each. There's multiple earth screens per core, but there's one HFCT or one RFCT per phase.
Yep.
Yeah. No, per phase and per cable per phase. So every single.
Yep.
So there's multiple cables per phase, and each one was individually monitored.
Yep. No worries. So the UltraTurf Plus 2, so that's the handheld piece of kit that we have as opposed to the cable data collector. That can also take snapshots with an RFCT. So if you have an UltraTurf Plus 2, you'll see there's an RFCT in there. You can hook that into onto the earth screens of cables, and you'll capture PD signals bouncing up and down the cables, and you'll see what you can see there on the right hand side. You can see the phase resolved partial discharge pattern. You're looking for clusters that are 180 degrees apart along the sine wave and looking for certain patterns. And then the waveforms. You'll also capture those waveforms and those fast, high frequency pulses, and that will be all recorded by yourself or the user of that instrument to put in and later analysed in your software. You can also apply the filters into the UltraTurf Plus 2, and the readings come out basically the same as what you see on the cable data collector. Now with the UltraTurf Plus 2, the waveforms there don't show as much granularity as the cable data collector in terms of looking for distance to cable. So when we use the cable data collector, this is the information that we see. So in the top graph there, we see a phase resolved partial discharge pattern. We see two clusters of activity 180 degrees apart, which look like internal void PD. The second graph that you can see there is the waveforms, and that's the pulses that I've been talking about that are bouncing up and down the cable. You can see the initial pulse, the distance to the first, or distance to the PD side. The third one is the total length of the cable. And the bottom one where it says cable map, that's where we actually map out those distances and see where all the different PD events are occurring. in reference to the total length of the cable. So this is a case study. This is a real life case study where we've got a 1.4 kilometre long cable. It's both paper lead and XLPE cable, and PD was identified at 56% of the cable's length from where you're testing. Okay, so just over 700 metres, 750 metres, whatever the maths is on that. What we're talking about here is this is your unfiltered data. There's two high pass filters that we apply to the data, which help us A, detect if there's PD occurring, B, it will get rid of noise. As I said earlier, usually there's a lot of electromagnetic noise on all our high voltage cables out there because your system's connected to everything and signals are bouncing off everything. So we use the filters to see through the noise so we can see PD, but we also use the filters to be able to see the higher level filter that you apply, the less distance down the cable you can see. So we use that information to our advantage as well. So if I go to the next slide, this is the exact same test, but it's with the 500 kilohertz high pass filter applied. What we see when we apply the 500 kilohertz high pass filter is our ultimate amplitude levels of piccocorns drops down. So the PD doesn't look as bad, even though it's the exact same PD. And our waveform shapes actually start to lose their energy because everything starts to propagate, and we're not capturing the lower frequency components of the PD. And then as we apply the 1.8 megahertz high pass filter, it makes it quite difficult for us to see. If you look at that waveform graph there, it makes it difficult for us to see a distance A to the far end of the cable and B where the PD pulses are bouncing up and down, and that's because we've chopped out a lot of the information that we required. So it's quite fortunate on this cable that there wasn't much noise around, and the PD signals themselves were quite strong. So even if there was noise around, the PD signals are stronger, so our instruments captured that quite well. So those three filters, unfiltered, 500 kilohertz and 1.8 megahertz, that can also be applied with your Ultra 2 Plus 2 device, and we always advise capturing all three filters every single time to give yourself the best data and the best chance of finding PD. Okay, so we've got a case study here. Testing on an interconnected 22 kV underground network. So here we have two example substations, but this was a case study of a job that was conducted recently where we had multiple substations throughout the streets, distribution network, 22 kV, and everything's connected to everything. So the job was to figure out whether there's any PD on the cables, also at the substations. So what we do at both these substations, there's a cable that runs between these two, is we test everything for TEV activity. We test everything for ultrasonic activity. So if you do find ultrasonic, it's probably inside the switchgear. It could be the terminations themselves. You could have a defect in the HV fuse box there somewhere. But we didn't find any ultrasonic. But what we did identify was on the white phase cable at substation A, a defect, and also on the one of the white phase cables at substation B, another defect. So the data from that is shown on the right hand side there. So what you've got is on substation A, you've got 35 decibel source, 3.95 pulse per cycle, and you've got a phase plot there indicating definitely one and potentially another phase worth of discharge. Then at substation B, we see quite a similar trace, but that also is indicating discharge. So if we were to stop at that point and we weren't thinking about the network connected as a whole, what we may end up doing is saying, right, you've got some cable terminations or potentially a bushing or a defect within an RMU at substation A, and then also at substation B, we've probably got a termination or a bushing or an internal to the substation defect, and we could end up making a misinformed or misdiagnosis. A misdiagnosis. misdiagnosis because we're thinking that there's two different PD sources. So what we do at that point is we have extra instrumentation to help us. So one of the things we use is called an Ultrasound Locator. So the locator was used on those cable terminations to figure out, using the TEV time of flight method, where the TEV signals were coming from. And in that instance, you're either going to figure out if it's coming from inside the substation or if it's coming from down the cable. So we ran that test at substation A, and it was saying these signals are coming from down the cable. So at that point, you discount the substation. The substation's most likely okay. And then you do the same test at substation B. At substation B, it was also pointing down the cable. So it's like, at that point, we go, well, we've probably got some cable PD. Let's investigate further. And then at that point, we were able to connect the RFCT onto the earth screens of those cables at both ends. Again, we picked up a very similar phase plot, as you can see on the left-hand side there. The top one is substation A and the bottom one is substation B. On the right-hand side, you can see those waveforms. So this is giving us good indications that there's PD on the cable. With that waveform there, you can see a nice unipolar pulse. Unipolar means that it's not just ringing up and down like noise. There's a sharp shoot up, and then it sort of levels itself out. And then we get out the cable data collector. So we test the cable from both ends of the cable at the substation. So at substation A, we see the data that's on the top graph there, where we've got the phase plot on the left-hand side, and then we've got the waveform on the right-hand side that we analyse to figure out where the PD is coming from. So we can see that from substation A, we're getting a distance of around 74% of the cable's length. In this instance, the cable is 76 metres long. So 74% of the way, or 56 metres away from that substation, we're seeing PD signals. And then when we test from the other substation, we see a similar phase resolve pattern again, and we see 20 metres from that substation back the other way, we're getting a good indication that there's PD signals emanating from something there. So at that point, we look up all the cable history, the cable data, and we see if there's any joints along that section of cable. And there was one joint located around about 20 metres away from substation B. So the recommendation from that job there was to look into that and consider what you're going to do about that. We can also, our amplitude levels, as you can see on the left-hand side there, was 6,000 picocolumns at unfiltered data. So that's the true level of picocolumn. So when we relate that back to the table that Neil showed earlier, 6,000 picocolumn is in the red level. So it's a defect that should have a high priority on it. And so what I've just shown you there is the use of multiple instruments and using the knowledge that you're working on an interconnected network and cables run from substation to substation to substation to substation. When you have signals, you need to be able to track them down and figure out where they're coming from. And the use of all your instrumentation is how it's done. Okay, so I'll hand over to Neil now, who's going to run through the summary of the work.
You just finished answering that one.
Okay.
I think it's ready to go, just sent.
Okay.
Okay, so summarize on that. So it's an interesting area. I've been doing a lot of the PD testing for many years, and the difficult, always one of the most difficult things has been, is it when you find something around the cable termination, is it the cable, is it the cable termination, is it the bushing or something that's further on? It's always the tricky question. So what we've been shown and what Brad has shown in this particular case is that we deploy different techniques to try and figure out. We also use a bit of engineering judgment and knowledge in terms of history of failures, type of switchgear and things like that, and also pattern recognition on the phase resolve plot. So sometimes we can see from the pattern that it may be associated with a defect up in the switchgear, for example. The cable terminations, if you've only got cable terminations, you haven't got joints in between, then generally you don't need to try any harder than using the methods that we use, the handheld TEV and ultrasonic methods for testing. If you've got a relatively small network or relatively small sections of cables and you haven't got access to the cable earth to place a HFCT on, again, just doing the TEV and the ultrasonic will get you a certain way. You can see from the example Brad showed, we've got a 76 meter long cable. We've got discharge 20 meters up. So on one substation, we're seeing almost as much levels of TEV, 34 dB, 56 meters away from the source of the discharge, as we are at the other side, seeing it 20 meters away. So signals will travel, TEV will travel. So if you haven't got access to that earth screen, at least carrying out the TEV and the ultrasonic methods will also start testing your cables to a certain extent. Certainly, maybe the transition joints from when you've cut in the new substation, you've got XLPE cutting into the old PILC cable, and you've got that transition joint maybe 20, 30 meters up. You can find that just by using the TEV and ultrasonic. We can't stress enough when you're taking this that everything is interconnected. Signals travel, as we've just shown. They will couple from one part to another. So if you've got a 10-panel switchboard and you want to test the cables, and you find signals on one circuit, and you only tested that circuit, you still can't be 100% sure at that time it isn't coming from adjacent circuits and being coupled in. So what we suggest is always to test everything. Try not to testing it as small sections or items in isolation, because it can cause misdiagnosis. So like the example Brad showed, if we just went to substation A to test substation A, we might go down the route of just replacing the terminations in sub A when it's nothing to do with that specific thing. If you can't access the cable screens, of course, then you can look much further down the cable. So the example again that we showed was a 1.4 kilometer long cable. We found the discharge very easily at 56% of that cable. That specific cable was allowed to continue on in service without any proactive any proactive replacement, and that did fail in exactly that same place within the next 1 or 2 years, I think, if I remember rightly. So the combinations of the different sensors, the techniques, allows you to start localizing and allows you to make the best use and to make the overall diagnostics. It can be true at times that you get indications of partial discharge on cables, and you can't, just from online techniques, come to the most specific answer, such as what Brad showed, which is that cable joint 20 meters up is discharging, and that cable joint will fail soon. Sometimes you do need to go and then maybe take an outage and take offline testing in order to do that. You can usually test offline cable testing, maybe one or two cables a day, three or four if you really set up and you've got outages on. Obviously, it takes outages, so it's a lot more costly. There's all the safety implications, the switching implications as well of doing it. So what the online testing can also help you do is target the more expensive, the more difficult question at the areas that is going to give you a better return. If we do all this, then as general with everything, what we can get is improved asset performance, greater reliability, and safety. We can lower the costs, like we said at the beginning. We can generally find that a third of the cost, we can save a third of the cost by proactively replacing cable joints that are discharging before allowing them to fail. And the big thing, one of the other big things that we've got here is we've got aging networks a lot of places. So what we can do by doing widespread testing, and you can do a lot of cables in a relatively short amount of time if you can get access to the earth screens using these techniques, that allows you to get an overall view of the condition of that network, and that allows you to understand, what may be needing replacement in the next 5-year period, for example. So you can start making the smarter investment decisions based on condition, because this is the area that we typically have less information on compared to other asset groups. That brings us to the end of the presentation. Brad is still furiously typing away on questions and answers. So if there are any questions, please shout out now, and we'll continue to answer for a while.
Let's try to answer everybody's questions. Sometimes the question doesn't.
Yeah, you just have to. Okay.
What's the max length of cable with the testing techniques you mentioned? Sorry if I missed a few.
Okay, you might as well write that. So this question that we knew was going to come up, and we didn't put the definitive answer in the slides because there isn't one. It all depends on a number of things. So how long a cable you can test is dictated by a number of things. If we've got an XLPE cable, signals will travel will travel much further, more readily, and it's usually a cleaner signal than if you're on a PILC type cable. And it depends on the amplitude of the discharge, how much noise you've got on that system, on the earthing, and the distance away. So you could see on the PILC cable example we showed, it was a relatively clean earth, so 1.4 kilometers up, and we were finding it 56% up. So let's 700 and so meters up, we were able to see it. XLPE, absolutely, you'll find that, and further along. We typically say 2 to 3 kilometers, maybe 4 kilometers on a quiet cable on PILC. And that was a mixture of XLPE and PILC, but mainly PILC. On an XLPE cable, you may go further, but it's a function of how big the discharge is. The bigger the discharge, the longer it will stick its head above the noise. So the type of cable, the amplitude of the discharge, and the amplitude of the noise are 3 important factors in that. But 2, 3, 4 kilometers is usually doable.
Okay. That is a good question.
Okay.
I don't know if you want to do that. Thanks for the informative presentation. That's what they're testing.
It depends on it. They'll take that one individually. So if you've only got one, yeah, we'll have to take that one individually. If the section of cable is a mix of PILC and XLPE, so we'll answer that individual. So if that section of cable has a mix of PILC and XLPE, how do we determine the fault locations considering the different propagation speeds? Good question, Stephen.
It averages out.
It does tend to average out there. You can do some relatively fancy calculations by looking at the different sections of the cable and seeing the propagation speed for one part versus the other part. Generally, if you think that you're only going to be, there's always going to be an element of accuracy and percentage-wise. There's also going to be a significant element of reliability of your cable records, in truth. So 1400 meters, is that really 1400 meters, or is that 1410? And where exactly are the joints? Typically, what you're really looking for is to look to find the location in the vicinity of a percentage. So if we say it's 56% up, and then you look at the cable records, and your cable records indicate that you've got a joint which is actually 57% up, and there's your likely source. Because you've got the you can see the 3 pulses, then again you know the time it actually takes for a pulse to go from one end of the cable to the other. So in relative terms, that will also even itself out. There will be a little bit of tolerance that you have to do, but generally, as long as you can see the end pulse and the beginning pulse, then your accuracy is going to be okay to at least localize to a joint or so.
Okay. And then we just got one last. I think we'll just take one last question. It's nearly 11:30. Can we make a direct comparison for the results captured between the +2 RFCT and the CDC?
Yeah.
Phase plots look the same.
Yeah, the phase plot, you can see on the example again that Brad showed, the phase plots are the same. The amplitude is generally the same. It's the same technologies ultimately, same sensors are used. So yeah, can you make a direct comparison? Then yes. The CDC is easier to do more detailed analysis and will capture more signals. So you're capturing generally 300 waveforms, 900 events using the CDC over a period of, typically for a 3-core cable or 3 individual phases being tested, it takes about 7 to 10 minutes to take a sample. For a belted cable, so 1 earth screen, it's about 1.5 to 2 minutes on average. So they're the sort of timing that you're taking. Whereas for an UltraTev Plus 2, you're generally only taking about, well, it only is measuring 10 seconds worth of reading. So you may get some slight variations due to that. But as you saw from the presentation, the actual pictures that you got from the 10-second reading versus the 5-minute or 10-minute reading were very, very similar. So very comparable.
Yeah. Can we install an RFCT to multi?
Yeah, so a belted cable or a single screen, yes, you can. The one thing that you're not going to be able to find when you're doing that is phase-to-phase type discharge, but that's typically not what you would get. So on a screen 3-core belted cable, you have 1 earth screen. The failure mode is typically going to be phase to earth, and you will find the 3 phase to earth. You won't know which specific conductor, but again, you're not really bothered about that. So yes, you can do it. So you just it works absolutely fine.
Yeah, cool.
Okay.
All right. The questions look like they've.
So if we've actually kept the time for once.
I was about to say it's right on 11:30.
If anybody does have any further questions, or you want something else, we've got our contact details up here. We're happy to take those questions. We're happy to take some. We've got one that we're going to take offline anyway, because it's a specific question for that company. So please feel free to keep in touch. You can email us, you can phone us up on this, and we've got the LinkedIn addresses there as well. If there's any other topics that you wish more information on, you think there's a good webinar, then suggestions are also welcome for that.
Yeah, definitely. Yep. So any questions, shoot them through to Neil and myself, or give us a call. We're here in Brisbane.
Yep.
Australia.
Yeah. Other than that, keep well, stay safe, try and prevent failures.
Yeah. There you guys.
Thank you. There's an end here somewhere.
I think you go file, the top file, and then exit, very bottom one.
End webinar.